So I did not have a chance during the session to go over some of these other problems. So let me just mention them. And they all have something to do with similar techniques. You get the impulse response function, write it as a polynomial, and then write that polynomial as a partial fraction. You see this question 6, unit sample response. Consider a linear time invariant system whose unit sample response is shown as below. Hn equals 1/2 n to the n minus n over 2. Now, we know how to convert this into a polynomial, right? You take h of 0 times 1 plus h of 1 times z or r, does h of 2 times r squared, and so on. Now, if you do that, you'll get an expression. It turns out that the answer here is yes. If you do some substitution, you should, hopefully you can see how you can write the resulting function as a geometric series. Okay, so you can do that. All right. Now this part B, is it possible to implement the system with a finite number of adders, gains, and delays, and no other components? Remember that the R becomes a delay, right? And then of course coefficients become gains, and then adders become adders. Okay, so if you look back at some of the examples that they already have and see what you have here, I think it's not too different from some of the ones that you've seen before. Okay. Right. Now, here we have a system whose unit sample response is n plus 1. He says, determine the poles of H. Same approach. Here you have the impulse response, and to get the result, well, you take your impulse response and you multiply the nth term by r to the n and sum. Right? Now, we have seen a similar series before. If you can't identify it, you can ask ChatGPT, probably, and it will give you the answer. But we have seen a similar series before. Right? And you do have the same approach. What you want to do is you want to get that. I mean, the series should be expressible as a ratio of polynomials. Well, basically, it's a polynomial in the denominator, and the poles are going to be the roots of the denominator. Or well, actually, it's 1 over the roots of the denominator. It turns out to be 1 over the roots of the denominator, because the denominator becomes 1 minus the constant times r. And you'll see that. Okay. Now for part B, part H can be written as the cascade of two identical subsystems, each called G. Determine the difference equation for G. Now, you will find out that this impulse response can be written as a square. Since it can be written as a square, that's the composition of two, rather I should say that's the product of two terms. The product of two terms is the same thing as saying you have the composition of two systems. So that term that you're squaring represents a single subsystem. And if you make two duplicates of that subsystem, then you will get the result. So let me show what I'm talking about. I don't want this. Okay, so I copied the question, and if you suppose h of z is equal to, let's just say, call it h1 of z squared. Okay, so h1 of z has a system represented by a system diagram. So the system diagram, the diagram for h of z is just going to be, you'll have the diagram for h1 of z, And then you'll also have an arrow here, and then you'll have the diagram for H1 of Z again. Okay, so whatever diagram this is, I don't know what it looks like, then another one for there. So to find the difference equation, you just need to identify H1 of Z and convert that to a difference equation. Okay? All right, so so that tells you how you're going to get the block diagram. The block diagram will have those two parts. So basically all you need to find is the block diagram for the H1 and concatenate it. Right? And then you can follow through a single impulse and see why this is the result. Basically what you should do is look at the output of the first block and then explain why the output of the first block gives you the second block. Turns out the output of the first block is all ones. It's a sequence of ones. And then when you apply the same operation to that sequence of all ones, you get this ramp function. Right? So be on the lookout for that. Right? Now, this one here, I'll let you read this. This may be a little bit challenging, but what you're going to do is you're going to take the expression for H and change it slightly, read how you're supposed to change it, and then do a partial fractions expansion of that result. Okay. And then this one here, this would be a computer problem. Well, yeah, you get a computer problem. You get the expression for, get the new small h resulting from this result, and just plot some values. All right, let's go on to 7. All right, now this one here, let's see, is there a 7 also, or is that was 7? That was problem 7. Okay. Now this one here, we didn't really talk about during lecture 3, so let me give you some background on this one. All right, I'll help you with this one. So we'll do problem 8. I think it's not fair for you to have to do this without having had the background, and I guess it's in the next lecture, but I'll give you a kind of mathematical perspective about what's going on. Firstly, the first two, because so far what we've been talking about are discrete systems and not continuous systems. But what he's doing here is he's taking a continuous system and he'll convert it to a discrete system. Okay? So here what we got is a mass and spring system. If you've done physics, you may be familiar with this. And so what you have is you have this, basically think of this as a rod that you're jiggling up and down. And as a result, the mass is moving up and down. This is not a fixed wall or a roof or anything. It's a rod that's moving up and down. That's why this x of t is a function of time. And the spring is going to the mass on the spring is going to move in response to that jiggling. Okay, so the mass is 1 kilogram. The spring constant is 1 Newton per meter. Don't worry about this. I'll help you with this. Assume that the spring obeys Hooke's law. I'll tell you what that is. And the reference positions are defined so that if the input x of t is equal to 0, the resting position of y of t is also 0. Okay, all right. So what you have here is a force. So the Hooke's law says that force is equal to minus the spring constant times the separation, or times the length of the spring, or I should say length deviation of the spring. What they says is that at the beginning, when x and y are 0, then there's no force. So that means the spring has its reference length. The deviation is the difference between the length of the spring and the reference length. Okay, so this is a difference from reference length. Okay, all right. So what happens here if I have this, and here this is my reference length. Now suppose I move suppose I move just y of t slightly. Okay. So this here is y of t equals 0. And this is x of t equals 0. All right. Now suppose I displace this a little bit. Okay. Okay. So this is actually going to be y of t, because y of t equals 0 is at this point. So this is going to be y of t. Okay. Now I'm not sure if he's measuring y of t to be positive or negative. It looks like y of t positive is in this direction and y of t negative is in this direction. Okay. So actually, this y of t is going to be negative. So we need to make sure that we understand how that works out. All right. Now, so that means that the deviation, in this case, the length deviation, well, it's the difference between the spring is now extended this far. Okay. So it's that much longer. So the length deviation is equal to y of t. Okay. Now, if I move x of t also, so let's do a more general picture. Suppose I move x of t as well. All right. So if I move x of t as well, so here's my reference position, x of t equals 0. Here's my reference position, y of t equals 0. Okay. And then I move my x up to here. So let me just call that x of t prime. Okay. And then suppose my y of t prime is something down here. Okay. All right, what's my new length? So this was my reference length. My new length is here. Okay. So in this case, the length deviation, well, if x is positive, that making it longer, so it's equal to x of t prime. And then when the y becomes more negative, that makes it longer, so it's minus y of t prime. Okay. Okay. So the force is going to be proportional to this, x of t prime minus y of t prime. So I'll just say the force on the mass, because we're talking about the force on the mass at time, and we'll just call it time t prime, it's going to be equal to x of t prime. Sorry, didn't mean to do that. Minus y of t prime. Okay. Now at this point you need to know Newton's law, which he doesn't say, but I'm telling you, Newton's law. Newton's law says that the force on the mass is equal to the mass times the acceleration. Okay. Now in this case the acceleration is equal to the second derivative of the position. And we're looking at y as our position. So it's the second derivative of y. And here I'm looking at t prime. Okay. All right. Sorry, I have this. It's this times minus k, right? Because Hooke's law says that I take the deviation times minus k. That's what I have up here, right? That's this here. Okay. All right, so my final result is d squared y dt squared, t squared. And I can say at t prime, or I can say at t. I can say at any value here. So I've been using t prime, so I'll say t prime. So that's equal to the mass. I'm sorry. The mass times the acceleration is this. Okay, and then this is going to be my expression from up here. Okay, so that's going to be, and I'll bring the minus k in front. Equals minus k times x of t prime minus y of t prime. Let's see. Does that make sense? I think I actually got the sign wrong here. This is going to be the negative deviation. This is actually going to be a plus. Okay, because I know that because if y gets bigger, the force should become more negative. The force always is the opposite sign of the y. Okay, so this is the equation that it should be. So if I divide by m, I'll have d squared y dt squared is equal to k over m, or let's just say, well, I can just say minus k over m y plus k over m times x. Okay, or you can write that as d squared y dt squared plus k over m y equals k over m x. Now remember, these are all functions of t, or t prime, however you want to do it. I think I'm going to go back to t. Okay. All right. So I think that's actually the answer to part A. All right. So I did part A for you. Okay. Yes. Okay. Now you also need the initial conditions. It says that there are no initial conditions. Now step response. What is step response? Step response is the condition when, so I'll just tell you what step response is, and I'll give you an indication how to solve that. Okay. Solve this differential equation. So I'll just say the same equation again, d squared y dt squared plus k over m times y. And I think these numbers are 1, so it turns out to be 1. That's nice. Now here it's step response means that x of t is equal to 1 when t is greater than or equal to 0, and 0 when t is less than 0. Now that's the same thing as saying d squared y dt squared plus k over my equals k over m, okay, for t greater than 0. And then I also have y of 0 equals dy dt at 0 is equal to 0. Okay? So that's what you want to solve. You have this differential equation, and then you have these two conditions on y. All right, now to solve, I'm going to assume y has the form, let's see, I want to do particular solution plus homogeneous solution, just like before. Okay, so y particular plus y homogeneous. Okay. All right, now the particular solution, we've seen before that particular solution is always just plugging in a constant. So see if you can figure out how that works. Okay, so that's the particular solution. Then we want to say, so then you can show that y particular, that y homogeneous, of course, is equal to y minus y particular. Okay, and if you plug that back in, or I mean that's the same thing as saying y equals y homogeneous. Well, that's what I have up here. If you plug that back in, you will find that d squared dt of y homogeneous plus k over m y homogeneous is equal to 0. Okay? So what you should do is assume, all right, now you can go through and try to solve it, but we're going to build on the shoulders of giants and use what we know about this type of problem that will assume that y homogeneous has the form a exponential of b, well, a1 b1t plus a2 e to the b2t. Okay. Now, b1 and b2 will be complex. Okay, they will be complex. But you can use this fact, use that e to the I, or he says j. Okay, I'm going to use j for the complex here. So e to the j, well, e to the aj at is equal to cis of at. So it's equal to cosine of at plus I sine at. All right. So once you get your complex roots here, you can substitute the complex roots for this. Actually, I used an I here. I'll use a j there. Okay. Okay. So you'll substitute this for your complex exponential. And that should give you a solution. All right, let's see if there's any more to the problem. So that's the step response. All right, then he converts this to a derivative. Okay. All right, so let's see. So he says, differential equation part contains a second derivative if you did part A correctly. We wish to develop a forward Euler approximation for this derivative. One method is to write the second order differential equation in part A as a part of first order differential equations. Then apply the forward Euler approximation to the first order derivatives. Right. So what's he talking about here? Okay. This is also a standard approach to higher order differential equations. Okay. All right. So what you do here is I can write this as, so my equation here was d squared y dt squared plus, what was it, k over m or m over k? K over m. Y is equal to k over m. So I'm going to break this up into two equations. Okay, and the two equations are dy dt. I'm going to write a z. I'm going to write on this side. I'm going to define a new variable. Okay. Now, since z is the first derivative, this d squared y dt squared, that becomes dz dt, right? Because I'm taking the derivative of the derivative, right? And then I can write the other ones on the other side. So that's minus k over m y plus k over m. Okay. So for these two derivatives, I'm going to substitute. Here I'm going to substitute dy dt equals, and what was the substitution that he gave me? Y of n plus 1 minus y of n over t. And then here I'm going to substitute z of n plus 1 minus z of n over t. Okay? Okay. Now, so basically what you'll do is you'll find the z here from here. So z is going to be equal to this, and you plug this value in for your z here, and you'll get another expression. All right? And then you just put that all into here, and you're good. All right? And then you do the same thing. This part D is similar, just a different expression. Same approach, just different expression. In fact, what you'll get is this and this. You will actually get these two results. Okay. Okay. And then let's see. This one here. So they do a compromise. This one is for. Notice that this has n plus 2, n plus 1, and this one has n minus 1, n minus 2. So these are the ones before. These are the ones after. So a centered approximation means you just take the one in the middle, right here. It says use this approximation to determine the step response of the system. So in this case, when he says step response, he means the impulse response, because you're going to so for this one here, if I'm understanding this correctly, it's possible I'm not understanding this correctly, but I think this is right. Let me copy it here. Okay. This is part E. Okay. So what you want to do is you want to you'll get a difference equation. What you'll do is you'll get a difference equation relating y, and x. Sorry, y. Yes, you'll get a differential equation relating y and x. Okay, then you will. Then you want to do it. What you want to do is convert that to a polynomial equation. And in fact, the way you do that is y of n plus 1 is equal to delay of y, right? And r of n minus 1, no, y of n minus 1, sorry, is going to be r inverse. Okay, and you can think of this r as a algebraic variable. No, I think actually he usually does capital Y's. Well, I mean that's what you're actually going to replace this with r times capital Y, and then this is going to be r inverse times capital Y. Okay, so that changes your differential equation into a polynomial equation, and then you just want to go ahead and find the system response. Okay, so the system response will be the polynomial. Okay, so that's my wrap up for this problem. Okay.